Yes, all right. So it is apparently recording. In any case, so there was some kind of a connection problem. But in any case, in summary, I mean, this is just an example. It's an example of a continuous group. It's an infinite group, but it's a compact Lie group. And so somehow it appears that this particular representation is also reducible. All right, which one? It is this one. This one is also reducible. It turns out that all of the representations of irreducible representations of SO2 is one-dimensional, and so therefore any two-dimensional representation can actually be reduced. And so as a result, I mean, this is just an example of that. Okay. Turns out that the O2 is not reducible.
Sorry, can you show the bottom
consider
again?
These matrices, I mean the corresponding orthogonal matrices, as I mean, extend this representation to the bigger group O2. O2 is not an abelian group. In that case, it turns out that I mean, these are not, there are no invariant subspaces, so therefore this is an irreducible representation of O2. Okay. Let me say it like this.
Jerome, can you show the bottom part of the page again?
I don't know if anybody has any comment or question. Yeah,
I think you can hear us. Okay.
So let me then pass to the third example. All right, this is actually, it's not part of this course because of the reasons that I'm going to explain. Right, this is some kind of a strange representation. So this is a translation group. It's one of the groups that we actually meet in physics. It's a translation group. It's the one-dimensional translation group. So as a result, I can think of these that group as basically the set of real numbers with addition as the operation. But in any case, the translation is essentially you can think of it as some kind of an operation. So it has these properties that whatever there's a function. Yeah, you can think of the translation by A as some kind of a function applied on some coordinate and just translate it like that. And what happens is that the composition of these two translations is equal to a single translation with parameter A plus B, for example. In any case, so it turns out that this group has this kind of a two-dimensional representation. Okay. Just check that this is a representation. Check that this TA, this matrix multiplied with TB is of the same kind of a matrix where the parameter, this parameter in here is basically simply added up. All right. So therefore, T is a representation of the translation group. However, this group is not finite. All right, let me add this. G is, all right, let me write it down. G is equal to R plus is not a finite group. Right? It is not a compact Lie group. It's not compact. It's not a compact group. Let me say it like this. It's a non-compact Lie group. Right? But it is a non-compact Lie group. Okay. What's the significance? It's not finite. It's not a compact thing. So in that case, we cannot use this this thing called this theorem that says that every representation is similar to a unitary representation. So that's not true anymore. So that means, let's say it like this: the representation T, this representation that we have written in here, may not be equivalent to a unitary representation.
May not be or cannot be. Oh, you can't hear me again. Okay.
It is not, all right? It's not equivalent, right? So there are some problems in here. So let me also write down the representation also in here. So that's 1, 0, A1. It's actually an upper triangular matrix, but I'm going to tell you something more about this. Yeah, there's a comment. There's a chat. You can't hear us right now. Why can't? Can you speak again?
Can you hear me now?
Yeah.
Okay. I was asking that. No problem at all. May not be or cannot be. I was asking.
Is not.
Is not. So there is no chance to be unitary, right? We are implying that.
For this one, yes.
Yeah. Okay. Thank you.
Let me say it like this. I mean, remember the theorem that I have proved. Right? If the group is a finite group or a compact Lie group, then every representation is equivalent to a unitary representation. So what I'm saying in here is that this theorem doesn't work in here anymore because this is not a, it's a non-compact Lie group, right? So the theorem doesn't work. So, but it may happen that this group might have some representations which are equivalent to a unitary representation. That's okay. It must have, it has actually some representations. This particular representation isn't one of those. So this is not equivalent to a unitary representation. So let me say it like this. So in a moment, I'm just going to also say other things. So may not be. Well, let me say it like this. I can replace it, is not. But I think I'm not going to prove this, but this is something that you can easily argue that this is the case. So it's not a significant thing, actually. Some group has a representation which is not equivalent to a unitary representation. So what? There's nothing significant in here. But in any case, let's ask to us this question. So is this representation reducible? Or is it an irreducible representation? The answer is yes. Let's remember the definition of reducible. It has an invariant subspace, which is non-trivial. Why? Well, I just look at this first vector in here. Just notice that this TA applied on E1, am I doing the calculation wrong? Yeah, is equal to E1. Okay, so therefore, let's say it like this, V1, which is defined as the linear span of E1. I mean, all of the vectors where the second entry is equal to 0, right? Think of it like this, right? This is an invariant subspace of the representation, okay? So since T has an invariant subspace, it is reducible. Well, is it decomposable? Let me say it like this. Is there any other invariant, sorry about this, non-trivial invariant subspaces? Okay, so the answer is no. It turns out there isn't any second invariant subspace, okay? So, I mean, you can show this by yourself, right? I suggest that you try these other possibilities in there, right? Can there be other invariant subspaces? So there are these trivial ones, which basically says that the 0 vectors, the null space, this is invariant, and the full space is also invariant. And then we have this particular space, which is also invariant. So therefore, can there be any other? Just show that by yourself that this is not, there are no such invariant subspaces. Okay, so unitarity is basically something that we have used in here. We have said that if there is an invariant subspace, if the representation is unitary and there is an invariant subspace, its orthogonal complement was also invariant. I cannot use this anymore in here because T is not unitary. It's not even equivalent to a unitary. So if it were equivalent to a unitary, then I would also somehow use this to actually obtain some other different invariant subspace. I cannot do that. Okay. So therefore, as a result, you can basically put the matrix into that form. So that means TA is not decomposable. Okay, so that means, therefore, TA can be put on the form. Let me say it like this. There's some kind of a similarity transformation. Sorry about this. This is S inverse TAS. I can put it into this form where these entries are equal to, are probably non-zero, but this is 0. Yes, it can be put on this form because it is reducible. How? But it's already in that form, right? So I know that it's already in that form. So therefore, I don't need to carry out any non-trivial similarity transformation in here. So it can be put in this form because it is reducible. But TA cannot be put on the block diagonal form. Right, so that means, let's say it like this. There is no matrix, let's say R, such that this transformation, if I do a similarity transformation by using R, I get a matrix in this form where these off-diagonal entries, both of the off-diagonal entries are equal to 0. Okay, so, right, there is no such R, no matrix R, so that's not possible, right? In any case, it is reducible, so therefore it is of that form, but it's not decomposable. And once this is the case, if it is not decomposable, in that case, sorry about this, let me think about this for a moment. This actually kind of tells you that the representation theory of such kind of matrices are actually quite difficult because you have some kind of strange representations like that, right? I think I'm just past my time, but let me complete this, and then after that, I'm just going to give you a 15-minute break, right? So as a result, let's remember that the translation group is an infinite and a non-compact group. So therefore, there are some undesirable features in the representation theory of such groups. Their representation theory is quite difficult, right? But we are not going to do these because we are not interested in these kind of strange things. I don't know if this kind of representations have any application in physics. So we don't care about these. What we care about is essentially the finite groups. That's what I'm going to concentrate on, and the well, some perhaps Lie groups basically. But this is something else, so it's not within the scope of that thing. In any case, let me quickly show that why this is not possible. Right, there's a very nice way of doing this. So let's just remember that this TA is upper triangular, is triangular. It's a triangular matrix. a triangular matrix essentially implies that, I mean, all eigenvalues of a triangular matrix are diagonal entries. So I can, well, just show this by yourself, right? Eigenvalues of all triangular matrices are equal to diagonal entries. Okay. So that means for this TA, the eigenvalues are 1 and 1, so there are no other eigenvalues. So you can just form the characteristic polynomials, for example. This is quite easy to see. So that means eigenvalues of TA are 1 and 1. Both eigenvalues are equal to 1. I mean, 1 is an eigenvalue with multiplicity 2, so it doesn't have any other eigenvalue. But it turns out that TA has only one eigenvector. But in any case, it's not diagonalizable, basically. So suppose there is an R such that R inverse TAR is basically something like this. So there are some diagonal entries in here and 0 entries in here. So I know that the XY are just basically the eigenvalues of this matrix in here, because for a diagonal matrix, the eigenvalues are the diagonal entries. And so therefore, this has to be the eigenvalues of this thing. But we know that the similarity transformation doesn't change the eigenvalues. So therefore, this has to be equal to the eigenvalues of TA. But I know that both of these eigenvalues are equal to 1. So therefore, that implies that these two diagonal entries should be equal to 1, right? Let me add again. Similarity transform doesn't change eigenvalues. Okay. So in that case, I have a situation where this matrix is similar to identity, therefore. So TA is similar to identity, but in that case, this implies that you can do the similarity transformation in the opposite way. So it's the similarity transform of the identity, but this is identity, right? Sorry about this. This is identity, so therefore this is a contradiction. So this is not possible if the parameter A is non-zero, right? So this is the way that you can show that. I think this is the easiest way that you can show that this TA this is not a decomposable representation. You cannot actually make this block diagonal, because making it block diagonal implies that you make it diagonal. In this case, by using this argument, you can show that this is not possible, right? In any case, let's stop here. So I said that I'm going to give a 15-minute break. So that means like 40:55. So let's meet at 11:55. So. Okay. So I'm going to stop the recording.